Now we'll discuss hierarchies of functions. So, you may be familiar with these common expressions such as polynomial functions grow faster than logarithmic ones, logarithmic time algorithms are better than polynomial ones. It turns out we can prove these formally, and the textbook Theorem 21.5 gives that formal proof for that. Similarly, exponential functions grow faster than polynomial ones, or polynomial time algorithms are better than exponential ones, can also be formally proven, and it's Theorem 21.7 in the required textbook. The proofs both use the limit rule and repeated application of L'Hopital. It turns out that these proofs actually give us tools when we want to compare the order of growth of functions. For example, when we want to compare the running times of algorithms. So what we can do is we can create bins of functions that are sorted by the growth, by the hierarchies of functions, and then sort within the bins. So exponential functions grow faster than polynomial ones. We can actually sort all the polynomial functions and then sort all the exponential functions. And because of those theorems, we already have a sort across the bins. Whenever we're in doubt with any functions, we can always just compare all the functions that we want to sort in order of growth by applying the limit rules. To do so, we take the ratio of the two functions and check whether the numerator or denominator is larger, and we can just apply limit rules directly. Now let's work on an example. So in this example, we are going to rank the following functions from the smallest to the largest in order of growth. And to do so, we're basically going to start by applying the theorem that we had just learned. So we can create bins, and we can have a constant time bin, we can have a logarithmic time bin, we can have a poly time bin, and we can have an exponential bin. And so our first task is to place all of the functions in the bins where we think they belong. And this binning is somewhat loose because sometimes some functions won't fit perfectly into either bin. They're sometimes in between, or they're greater than the largest bin. So we just try our best effort, and then we can correct once we have everything in a bin, because that does some of the work for us. So oftentimes we put the bin for each function is going to be the greatest lower bound in which they fit. So let's discuss that. So our first function is log n to the n. When we simplify this, this is going to be n log n. So since it's at least n to some constant 1, we can put it in the poly bin. So I'm going to put n log n in the poly bin. Then n squared is poly. N to the log n, not really quite sure. So a log n is greater than constant, but I'm not quite sure if it's greater than exponential. So what I'm going to do is I am going to put it in exponential, because I know it's greater, but I'm going to add 2 to the n because I'm not quite sure. I think this might be one of those that's in between. Then n log n, I'm going to put in poly because we have that n term. Then 2 to the log n. It's tempting to put that in exponential, but then we have to remember that the logarithmic functions and exponential functions are inverse, especially when we consider that computer scientists often leave off the log base 2, and when we're dealing with asymptotic notation, the log really doesn't matter, it just differs by a constant. So we are going to remember that 2 the log base 2 of n is equal to n, and put that in poly. then log squared n. So recall that log squared n is log of n times log of n. So I'm going to put that in the logarithmic function. And then I'll put n to square root of 2 in poly because that's a constant. And exponential 2 to the n I put in the exponential bin. So now we have to get to work in terms of sorting within the bins, and we can do that right now. It just so happens that the binning gives us a pre-sorting because we have the bins going from smallest growth to greatest growth. So constant all the way up to exponential growth is the greatest. So we have no constant, so we know our smallest is going to be our only logarithmic function. Now we can start working within poly. So within poly, the smallest that we have is n. And then we need to compare the functions that have n and also logarithmic functions. So now we're comparing n log n and n log n. So when we do that, we can look at what is the log is being taken up. So n log n is going to be smaller than n log n because we're taking the log of n, and n log n is just taking the log of n. So let's see, we have n log n is going to be 3. And then n log n is going to be 4. And you might be wondering, how do I know that like n log n is going to be growing slower than, say, n the square root of 2? And we can apply the limit rules for that, because once you apply the limit rules, you would have a logarithmic function over a polynomial function. For example, if you had n log n divided by n the square root of 2. So that's where that comes from. Now when we compare n the square root of 2 to n squared, we can just look at the powers we're raising n to. So square root of 2 is less than 2 in terms of constant, so we're going to label that 5 and label that 6. Now we have to deal with n log n, for n raised to the log n versus 2 to the n. And when we consider that, we can just apply the limit rule. So let's see. And we'll recall this is an indeterminate form. It's infinity over infinity, but when we keep on applying L'Hopital's rule, we don't get any place fast. So for this, we can remember that we can take a continuous function such as the log and bring it into the limit. So in order to compare this, we can take the logs of each. So here we are going to take the logs. And when we do that, we get log squared n versus n. And we see that n is going to be growing greater than log squared n. So here we have n to the log n is going to be our 7th largest, and 2 to the n is going to be our greatest function. That's going to be our 8th largest function. And what that also shows us is that n to the log n is greater than polynomial, because a logarithmic function is greater than a constant, but it's less than exponential.